State and prove the Weierstrass Approximation Theorem. Every continuous function defined in a interval can be approximated to the uniformly by a sequence of the polynomials. Now proof: if a equals to b, the result follows by the taking Pnx to be a constant polynomial defined by Pnx equals to f of a for all values of n. Without any loss of the generality, we suppose that close interval ab equals to close interval 0 to 1. Now consider capital F of x equals to small f of x minus small f of 0 minus x into f of 1 minus f of 0. 0 is less than equal to x is less than equal to 1. Here capital F0 equals to 0 and capital F1 equals to 0, and if capital F can be expressed as the limit of a uniformly convergent sequence of the polynomials, then the same is true if small f, since small f minus capital F is a polynomial. So let us assume that f of 1 equals to f of 0 equals to 0. Let us further define f of x to be a 0 of 0 for x without close interval for x outside the close interval 0 to 1. Thus f is now a uniformly continuous on the real line. Let us consider the polynomial Qnx equals to Cn into 1 minus x square whole raised to power n, where n equals to 1, 2, 3, so on. Equation 1, where Cn is such that integral minus 1 to 1 Qnx dx equals to 1, where n equals to 1, 2, 3, so on. Equation 2, since Qnx equals to Cn into 1 minus x square whole raised to power n, so integral minus 1 to 1 of Qnx dx equals to integral minus 1 to 1 of Cn into 1 minus x square whole raised to power n dx, which employs 1 equals to integral minus 1 to 1 of Cn into 1 minus x square whole raised to power n dx equals to 2Cn integral minus 1 to 1 of 1 minus x square whole raised to power n dx is greater than equal to 2Cn integral 0 to 1 upon square root n of 1 minus nx square dx is greater than equal to 2Cn into x minus nx cube upon 3 limit 0 to 1 upon square root n greater than equal to 2Cn into 1 upon square root n minus n upon 3n into square root n greater than equal to 2Cn into 3n minus my n upon 3n into square root n is greater than equal to 2Cn into 2n upon 3n into square root n greater than equal to 4Cn upon 3 square root n is greater than Cn upon square root n equals to 1 is greater than Cn upon square root n, which implies Cn is less than square root n. Equation 3, it follows that Qnx is less than equal to of square root n into 1 minus delta square whole raised to power n, where delta equals to delta is greater than less than equals to x is less than equal to 1. Equation 4, and as such as q and x tends to 0 uniformly for delta is less than equal to x is less than 1. We now write p n x equals to integral minus 1 to 1 f of x t into q n and t dt. 0 is less than equal to x is less than equal to 1. Equation 5, integral minus 1 to minus x f of x t into q n t dt plus integral minus x to 1 minus x f of x t into q n t dt plus integral minus 1 integral minus 1 minus x to 1 of f of x t into q n t dt. Since modulus x is less than equal to 1, we have minus 1 is less than equal to t is less than equal to minus x, which implies 1 minus 1 plus x is less than equal to x plus t is less than equal to minus x plus x. So this minus x plus x equals to 0. So which implies minus 1 plus x is less than equal to x plus t is less than equal to 0. So that x plus t lies outside the closed interval 0 to 1. Therefore f of x t 0, and hence the first integral on the right vanishes. This integral vanishes. Similarly, the third integral also equals to 0. Third is also vanishes. We remain with this integral. Hence p n x equals to minus x to integral minus x to 1 minus x of f of x t into q n t dt. So equals to integral 0 to 1 of f of t q n t minus x dx. So that Pn is a polynomial in X. Now we shall show that Pnx converges uniformly to f on closed interval 0 to 1. Since f is a continuous on the closed interval 0 to 1, which implies that f is bounded and uniformly continuous on closed interval 0 to 1, then for every epsilon greater than 0 there exists delta is greater than 0, such that for any two of the points x, y in closed interval 0 to 1, such that modulus f of x minus f of y is less than epsilon point 2, where modulus x minus y is less than delta is less than equal to 1. Equation 6, let m equals to supremum of modulus f of x. Equation 7, we have modulus of p n x minus f of x equals to modulus of integral minus 1 to 1 of f of x t q n t dt minus f of x equals to modulus of minus 1 to 1 f of x t minus f of x into q n t dt, because integral minus 1 to 1 q n t dt equals to 1 less than equal to integral minus 1 to 1 modulus f of x t minus f of x into q n t dt equals to minus 1 integral minus 1 to minus delta modulus f of x t minus f of x into q n t dt plus integral minus delta to delta modulus f of x t minus f of x into q n t dt plus integral delta to 1 of modulus f of x t minus f of x into q n t dt, which is less than 2m integral minus 1 to delta minus delta of q n t dt plus epsilon point 2 integral minus delta to delta of q n t dt plus 2m integral delta to 1 q n t dt using 6 and 7 less than equal to 2m square root n into 1 minus delta square whole raised to power n into integral minus 1 to delta dt plus integral delta to 1 dt plus epsilon point 2 using 2 and 4, which is less than equal to 2m square root n into 1 minus delta square whole raised to power n into delta plus 1 minus delta plus epsilon point 2, which is less than equal to 2m into square root n into 1 minus delta square whole raised to power n into 2 plus epsilon point 2, 2 into 2, 4m square root n into 1 minus delta square whole raised to power n plus epsilon point 2, which is less than epsilon for sufficiently large value of n. Thus, for epsilon greater than 0, there exists n independent of x such that modulus Pnx minus f of x is less than epsilon for all values of small n is greater than equal to of capital N, which employs limit n tend to infinity Pnx equals to f of x uniformly on closed interval 0 to 1, hence the proof.